It is a joint work with Gilles, Lago, and Francesco Gavazzo. And essentially, we are interested in the notion of equivalence for lambda calculus with continuous probabilities. So what do we mean by, what do we mean by programming with probabilities? Actually, we can mean two things. And the first idea, which is maybe more intuitive, is discrete probabilistic programming. So it is a program or a system that at some point in its execution can do probabilistic choice. So for instance, it is a random walk. So here you are in the state n, and with probability p, you can decide to go in the state n plus 1, but with probability 1 minus p, you can do another choice. So it is discrete probabilistic programming in the sense that what you obtain is discrete distribution. Now, what we are interested in this talk is actually continuous probabilistic programming, which means that you are able to talk about probability distribution over the reals. So more concretely, your program is able to sample from a continuous distribution, so for instance, a uniform distribution, a Gaussian distribution, etc. I mean, a uniform distribution, an interval, of course. And then you dispose of primitive function on the reals that allow us to handle the reals, the distribution, etc. So why do you want to do that? So it allows you to describe the behavior of system which operates on reals, and either which are inherently uncertain or which are deterministic, but we are not able to describe them in enough details, and so we replace that with probabilities. So we can, there has been a trend in relatively recently on continuous probabilistic programming, and there are well-life languages as Church, Anglican, Stan, etc., which have been developed. And so also an interest in the foundational side of continuous probabilistic programming. So it's part of that. So concretely, if we look a little more formally, it means that you take the lambda calculus, typically, and then if you want to add discrete probabilistic primitive, you are going to add typically a discrete choice here. So this program is going to behave as m with probability 1/2 and as n with probability 1/2. And when you want to do continuous probabilities, you are going to add a primitive sample, which is going to do the sampling typically in the uniform distribution 0, 1. You need to add all the reals to be able to talk about them, and then a family of primitive functions that additionally need to be measurable. Okay. And so the first problem is how to define an operational semantics. I hope you still hear me because I don't. Okay, thanks. And so to do that, first, to define a topological structure on the programs, which is inherited from the one on the reals, which means that if you have a sequence of reals that go towards R, and then you have a programs where this real occurs, so you obtain a sequence of programs, is going to converge towards these programs. Okay. So from there, since you have a topological structure, you obtain a measurability structure, which is generated by the open set, which is something very standard in measure theory. And so it allows you to talk about probability distribution on your set of programs. And so now the operational semantics, it is a distribution over the set of normal forms. Okay, so essentially in this talk, I'm going to consider a weak semantics and usually call by value, which means that the normal form are actually all the abstractions and the reals, etc. Okay, so it is an example of such a program. So what does it do? It just is going to sample in the uniform distribution, then it obtains the result, and it plays in here, where you do a real calculation using the real primitive functions. And then, this example here is interesting because it shows you that this program is going to transform the uniform distribution on the one here on a distribution which is essentially an exponential distribution, but translated from the one here, from one here, which corresponds to the addition. So it is an illustration on how, starting from just one continuous distribution and your primitive function, you can build all sorts of other distribution. Okay. So now what do we do with the programs? We want to compare them. So the idea is to check whether two programs are going to behave the same, no matter their interaction with the environment. And here we consider context equivalence, which means that the environment is going to be modeled by a program in the language, which gives you this definition, which is that two programs are equivalent when for every context, the distribution you obtain when you plug them is the same. And here, since you consider ground-type context, these distributions are typically distribution over wells. And you ask for the equality of distribution. So it is two examples. Here it is two equivalent programs. Okay, so here it exploits the symmetry of the uniform distribution because you obtain the same if you sample in this uniform distribution or if you do a symmetric thing. And so these two programs are going to be equivalent. Here there are two non-equivalent programs, okay, in call by value, because what you obtain here is that you are going to first evaluate, when you are going to evaluate these programs, you are going to obtain a distribution with probability 1/2 lambda x dot 0 and with probability 1/2 lambda x dot 1, which are two normal forms. However, here you are going to obtain a one-point distribution. And okay, it is a classical example of the fact that if your context is able to copy, it is able to distinguish if you do your probabilistic choice inside the lambda abstraction or outside the lambda abstraction. So this illustrates that. Okay, so the problem, okay, so this definition is well accepted, but the problem in practice is that you have a universal quantification in context. And so, here it is a proof that these two things are not contextual equivalent because I gave you a context. But here it is very difficult to show that two things are actually context equivalent. So what we do is that we look at the tradition of applicative bisimilarity, which was introduced by Abramsky, and where the idea is to express the semantics of higher order programs as the label transition systems, and then we exploit the intrinsic notion of equivalence in a label transition system to obtain an equivalence on programs. So how do we do that? The idea is that you consider an LTS with two kinds of states, programs and normal forms, and you have two kinds of action. One evaluation action that associate to a program's its normal form, and a family of applicative action where for every lambda abstraction and for every possible argument, you are going to do the substitution. And then, so what is the notion of equivalence on label transition systems? You are going to say that a binary relation is a bisimulation if whenever you have two states in relation and you do an action, but there and there, then you obtain two states that are still in relation. So this is a bisimulation, and we take as notion of equivalence the bisimilarity, which is the greatest bisimulation equivalence. Okay. And so this notion gave us a notion of equivalence on programs. So now if we look at the literature, what do we know on the relation between this new notion of equivalence that I just introduced and context equivalence? In pure lambda-calculus, the two coincide, no matter the reduction relation. In discrete probabilistic lambda-calculus, which means in the probabilistic lambda-calculus where you can do binary choice, okay, it becomes very interesting because it depends, the result depends on the reduction, on the evaluation strategy that you take. In call by name, okay, so you have one inclusion, but you don't have the other one, while the relation is fully abstract in call by value. And so the proof strategy for the full abstraction result here was to pass, was to use another notion of equivalence, which is logical equivalence. So what does that mean? It means that you consider logical formula here. So top is a formula which is always 2. There it is a formula which means that the state can do the action A with probability at least P, and then the formula phi holds, and it is just a conjunction. So this notion of formulas gives you an equivalence, since you can say, okay, two programs are going to be equivalent if, seen as the states of the LTS, they're going to, exactly the same formula is going to hold. And the interesting thing is that here you have an equivalence, an LTS, between the bisimilarity relation and the logical equivalence. So essentially they coincide. And so we use that to show that you have this full abstraction result. So now if you add probabilities on reals, so there was a first investigation by my co-authors, which was to show that bisimilarity is correct with respect to context equivalence. And on the other part, context equivalence is included in logical equivalence. And then the big open question was, are we able to show the full abstraction result also in the continuous case? And the natural way to do that would be to be able to show that also the logical equivalence and the bisimilarity coincide. Okay. So let's become a little more formal. So what is a transition system with continuous states? So the things in which we are going to model our language. So it is what is called a labeled Markov process. So you have a set of states, which need to be measurable, a set of action, and for each action, your transition function is going to become probabilistic, of course. So it means that for each action, you are going to say, okay, from each state, and for each measurable subset of the states, I'm going to say what is the probability when I start from these states to arrive here. So an example is maybe more clear. So here is the evaluation action for this program. And so, okay, this program is going to give all these programs there, but uniformly distributed. So how do we formalize that? For every singleton here, the probability to go there is 0, because there is no, the probability of arriving exactly there is 0, but if I look at an interval, in a sense, so the problem on that form with R in an interval, then I can express that the probability of arriving here is 1/2, for instance, if I take this interval here. I hope it's clear. Okay, so now the question is, can we look at this kind of system and say that logical equivalence for this system and bisimilarity coincide? And okay, unfortunately not. But the picture is a little more complicated. So the idea is that if I have sufficiently, okay, that's the idea. If both the labels are countable and the state space is analytic, it is the case. So if we consider the transition system for discrete probabilistic lambda calculus, the state is discrete. So in particular, it is analytical. And the labels are countable, since it is the set of all terms. And so in this case, of course, we have the coincidence of logical equivalence and bisimilarity. Now the problem is that here, now our state space is still analytical, simply because, our topology is inherited from the one of R, and R is very well behaved. But now we have a non-countable action space, because we have all the values that can be passed as arguments. And so, in particular, you have all the reals. And so, which means that we are here, and that it is not necessarily the case that bisimilarity and logical equivalence coincide. So what we like to do, we would like to define a class of LMP with uncountable action, where both the two equivalents coincide, and we would be able to put our particular transition system there. Okay. So a natural candidate has been introduced by Francesco and his co-authors, and because they were able to show the coincidence of the two equivalents for a particular class of LMP with uncountable actions. And how do we do that? How do they do that? They restrict the transition function with a continuity condition. So what's this continuity condition? They say, okay, I can define a function from a topological space into another by saying for each state S, I'm going to fix an action and a set of target states. And so what I obtain here is a function from state to 0, 1. And I ask this function to be continuous. Okay. And so it works well in the sense that they obtain coincidence of the relation. But for us, it doesn't work at all, because our transition system is not in this class. And to see that, the problem, intrinsically, is that some actions are going to be locally deterministic. And you see, if you have, for instance, a problem which is already in normal form, for example, lambda x.0, and I fix t as a singleton lambda x.0, then the probability to go from my state to t is 1. But if I change 0, if I change my program a little, for example, lambda x.r with r very close to 0, the probability to go to lambda x.0 is 0, since my action is deterministic. So there is no hope to obtain something like that. So what we do is that we are going to keep the idea of an additional continuity constraint here, but we are going to twist it a little with the idea that we're going to consider a topological structure on the set of distribution directly. So it is a notion of failure continuous LMP. What we do is that we consider the function that take a state and an action, and now we return the distribution. And since there is a standard notion of topological structure to the space of probability distribution, I can ask this function itself to be continuous. And which is interesting is that if you look at the previous idea of counterexample that I have just given, we see that here it works. I mean, if I take, for instance, the stationary one-action system over the reals, so to reals, you have just the identity actions, then you see that indeed it is failure continuous, while the previous condition didn't hold. Okay, so our results were like that. First, for failure continuous LMP, the two equivalents coincide. Then, if we enforce an additional constraint in our language, which is continuity of all primitive function and reals, the transition system we obtain is failure continuous. And so it allows us, in these restricted cases, to close the loop, in a sense, since here we obtain the equivalence of the two relations on the LMP, and so we can deduce a full abstraction result. Okay. Now, so this was the positive result. This is now the negative result, if you want, which is what happens when we allow possibly non-continuous primitive function reals. And an example of a very basic non-continuous primitive function reals is just a function that tells the equality, for instance. So it's not that exotic. And so what we obtain is that the two equivalents there didn't coincide, and we are not able to say if context equivalence and bisimilarity is the same. But in a more wooing way, in a sense, I mean, more wilder things happens. I mean, the measurability wild in an expression by Prakash Padangadan that I have taken here. And the thing is that context equivalence becomes a non-measurable relation, which means, for example, that the class equivalent on some program, some normal programs, becomes non-measurable. And then you have all sorts of problems, and we are not even able to show that bisimilarity can be computed locally, in the sense that we cannot even say, because the problem of the LMP is that he is infinite, he is uncountable, etc. And we are not even able to say, okay, I'm going to consider a program which is not very deep. I'm going to take a self-contained fragment that contains it. I compute the bisimulation, and then it extends to the bisimulation with all the system. Even that is not obvious. So things here becomes really very complicated. Okay, so to conclude, so the contribution of this work is first a full abstraction result for applicative bisimulation on an higher order language with continuous probability. It is also, more on the LMP side, a new class of LMP where bisimilarity and logical equivalence coincide. And it is a preliminary exploration of the case with arbitrary primitive function. Okay, so in future works, so one thing that would be interesting is that, okay, I have been a little quick at the beginning when I talk about probabilistic language, but something that people really want is to have Bayesian reasoning, which allows you to say, okay, I have some prior knowledge on my model, I'm going to do some observation, I'm going to update my model, etc. And so we would like to extend that to a language with Bayesian reasoning. We would like also to be able to do some quantitative reasoning, so to talk about applicative distances that have been considered in the discrete case, but not still in the continuous case. And then, of course, we would like to have more knowledge on arbitrary primitive function. Okay, thanks for your attention. And I hope it was